We're going to hear in our next talk from Andrew Webb, who is an associate professor at the Walter and Eliza Hall Institute of Medical Research and also founder of Ion Optics. As we've heard in our previous talks, that separating peptides is really critical to acquiring high quality data. And here we're going to get a crash course from Andrew Webb. So,
thanks, Jason. Ooh, it's loud. I'll talk a little bit quietly. So firstly, thank you, Nikolai, for the opportunity to give a workshop today. It's been a while since I've given a workshop. COVID sort of put a bit of a dent in that. I've actually travelled a... Ooh. Why isn't this working? No, here we go. Travelled a reasonably long way from Melbourne, Australia. This is where I live and work. I'm also here, I am representing Ion Optics today as a founder, and I act as the head of research there. I also have a few other day jobs, one being sort of the head of the proteomics for the Institute. This is where I lead the facility that services our Institute. This is our Institute. It is quite a large place. You may not be as aware in this audience about this Institute, but it has a reasonable amount of impact. We've got really a lot of amazing clinician scientists, biological scientists, primarily around healthy aging, cancer, infectious disease and immunology. We now have over 1,000 scientists falling into about 96 different laboratories. One of the things that I absolutely love about being a part of this institute, which I've been there for now just over 10 years, is the platform technologies there aren't just service environments. They're really operating as research labs. And this is where, as a lab head in a technology lab, I get to do research to support a lot of the other biological research that's ongoing. And this provided us with an opportunity that when we went and further developed some of the pooled emitter technology for chromatography, it enabled us to spin out this company, Ion Optics, which I know some of you who are already doing single-cell proteomics have been the beneficiary of as well. One of the other substantial benefits of being where we are located, we're on the precinct of the Royal Melbourne Hospitals. This is one of the major hospitals in Australia, particularly for adult trauma, and they specialise in quite a lot of areas. And I'll touch on a project towards the end where we're starting to sort of work and collaborate a lot more with the Royal Melbourne Hospital. So today I wanted to introduce, Nikolai gave me a title of, I don't think I sent you one, you gave me one, so I sort of have designed a talk around that, which is around sensitive chromatography. So what can we do from a philosophical point of view, from the theory, and also just to tell my story about how we came about as a company for Ion Optics. So my background is primarily in biochemistry. I was always a technological person working in a biochemistry lab. I postdoced in immunology and virology and more at WEHI. I've been a lot more exposed to cell biology and proteomics since. This is from 2007. I did postdoc in Imperial College for 3 years. And in 2011, I was recruited to the Institute as a senior postdoc. And it was quite unique that I got there not as a lab head, but I got there as a postdoc with no other lab head there. So since 2011, I've just been implementing my vision for what proteomics needs to occur or needed to happen. And this is really just described here by this blending of biology and mass spectrometry. We didn't want to be a hardcore lab, and we didn't want to just provide fee-for-service type things. So one of the things that became really apparent really quickly, because we had this research focus and improving the technology for biology, was that we were really limited in our chromatography to commercial columns. And mainly we were using Waters and Thermo. This is 75 micron ID. This is where we're using 400 nanoliters primarily. And we were using trap vented columns as well. And it was around sort of a few years later when we started really thinking about this, and it was sort of coincided with Joshua when he wrote this editorial talking about why chromatography is really important. And it was also at this time that I'd visited a few of the big labs. So there was a postdoc of mine that had visited John Yates's lab. I had visited Matthias Mahn's lab and saw that they were using packed emitter columns. And we thought, great, we've got to get into these packed emitter columns. It was pretty challenging. I think a lot of you have some of you in the audience have probably been packing your own columns and things. There was an 80% failure rate with the manufacture of these columns. The predicted life of these columns is pretty short. You generally only use them for a single study. And when I contacted the labs in Matthias Mahn's lab with a postdoc there, he said, yeah, you've got it. That's it. It's working. And I said, no, this is terrible. So for about 2 years, we we iterated on this technology, and we got to the point where we now have an ISO accredited manufacturing. So this is a scalable manufacturing method. Instead of having an 80% failure rate, we've got a less than 1% failure rate through the manufacture of these columns now. The lifetime of these, because of some of the improvements we've made to the pooled emitter process and the manufacturing of the emitter itself, we have a lifetime of more than 4 months. And recently we just heard from a customer at ASMS that have had a column running for up to 2 years now, and it just died, and he gave it a bit of a eulogy online. The other thing is we've now become incredibly good at creating the emitter tip to a very consistent. So now we're getting a very consistent signal run to run. And in some of our prototype columns, we've been seeing peak capacities up to 1,000. So this is something that you may see in the year ahead. So what can we learn from the sort of the classical chromatographic theory? You know, I guess the ultimate goal of what we're trying to do is to reduce this plate height. It's just literally the width of the peak, so that we can use the area under this column, and if we can fit it into a narrow peak, we can push it above the threshold of detection on the instrument. So we do have a very hard limit on all of our instruments, even trapping instruments, where the signal intensity really determines whether it can be detected or not. So the narrower the peak, the better the chromatography, the more chance we have of detecting this. Now, in classical theory, in chromatographic theory, this is the Van Deemter equation. It's made up of these different terms, the A term, B term, and C term, and I'll just walk through them quickly, but essentially all of them are just diffusional characteristics of how analytes move and behave in mobile phase. So the A term is just simply the eddy diffusion. It's simply that the path that the analyte will take through the column. You can see here this green line, you have a very small amount of diffusion here, whereas this lard, if you've got a rough packing in the material, you've got a non-uniform bead, you might find that your analyte will take a path like this. And what will occur is that you will get then a diffusion and a spread of your peak. What we can take from this is that smaller and more uniform beads reduce this plate height, reduce this width, and give us better sensitivity of that peak. The B term is simply the longitudinal diffusion, and this is just a dependency on the flow rate. So if you increase the flow rate, your analyte spends less time diffusing, you get sharper peaks. This is why when we run faster flow rates, we tend to have sharper peaks. And the last one is it's a little bit harder to explain, but essentially it's the size of your analyte and how it diffuses in the sample. Small analytes will diffuse a lot due to Brownian motion. Large molecules won't diffuse as much. And one of the things that this equation tells us is that when we start reducing the ID, we end up getting more efficient separation because we do have this diffusion across the full width of the column. So when you get down below about 100 microns, this is when for smaller molecules, particularly peptides, it's when you start getting this better homogeneity and more efficient separation. What all of this says from classical chromatography, that my biggest takeaway is that if we're thinking about and I'm always trying to think about improving things beyond what we currently have, bead size is the largest determinant of column performance. And obviously there's a caveat here that pressure increases by the R squared of the bead diameter. So as you go down, we hit fundamental limits pretty quickly. Our columns at the moment are running a 1.7 micron bead. I would love to go a lot smaller, but we're just limited by the hardware at the moment. The other thing we can do is increase the length of the column, and this is a little bit counterintuitive. By running a long column, you generally run a little bit lower flow rates. Generally, we would expect to have more diffusion because it's present within the column for a longer period of time. But with gradient chromatography in particular, it means that we do get a peak focusing continually through the column. So that means that we don't get a massive enhancement, but for a doubling of the column length, we would generally, and this is something that we've seen quite a few times, that we get about a 30% reduction in peak width. So there is a benefit to going to longer columns, but obviously you've got more volume, longer cycle times, you need higher pressure to drive it. And obviously the other caveat here is, again, pressure increases, but this time it's not it's in a linear fashion proportional to the cycle time. Proportional to the length of the column. So that's looking at the classical way of looking at chromatography is one thing, but when we're now interfacing our columns with a mass spectrometer, there's a whole lot of other things that we have to consider. And sensitive LCMS is incredibly complex. As we start getting, this is just a simple sensitivity chart. So if you take 1 as the value on the y-axis here when you're running 100 microliters per minute, as you go down, you can see that it almost follows the axes here. But if you zoom in, you can see here, as you get down to 10 microliters, down to this low flow rate, that you start getting this exponential kick, that you get more sensitive the lower flow that we go. And this is because of the ionization process. This is getting the ions in to the instrument itself. To really think about this, and this is sort of a culmination of a lot of thinking over a number of years, in trying to improve peak capacity, it's not just flow rate, it's not just column ID, it's all of these things interacting together. So what I've done here is just take all the different aspects that we think about when we're creating chromatography and link them to their dependencies. So you can see that this is a hugely complex process. You change one thing, you end up getting changes over somewhere else. So ultimately, it's sort of through this lens that we want to be able to design and improve our chromatography going forward. And just going back to this figure for a moment, so this is where we have this on a linear axis. What I like to do is think about these things in a logarithmic axis. And when you do that, you can see that we just have this nice straight line now from analytical flow, microflow, low microflow, this could be termed cat flow, nano, and also now into this low nanoflow. And I've got down here the column diameters that we can use. And at the moment, we are really, I would say, limited probably at this hard line here. But you can see here that there's a lot more improvement to be had going further down. We're not reaching fundamental limits in chromatography and separation and sensitivity yet. Just to plot where I think we are at the moment, I think current LC technology limits us to about here. I think the mass spectrometry technology has a lot more potential. And this is just a bit of a guess, stabbing the finger in the air type estimate. But with these fast trapping instruments, now we have these trapping TOFs, which are incredibly sensitive. I believe that with a bit of improvement in LC technology, we can certainly push a lot further and create a lot more sensitivity. There will, however, be an absolute limit here. So I've just put here a total ion current limit. And this is where at some point when you get through this ionization spray process, we're going to get to the point where there just aren't enough molecules to detect anymore, and we will reach this point. And it's my hope that in my lifetime that we reach this point. The other really nice thing about going to these lower flows, from an ionization perspective, there's a lot of great literature that talks about when you get down to these very small Taylor cones and the spray and the atomization that's occurring, you essentially have suppressionless spray. So you get very little interruption of matrix effects, and you get a very high resolution, get a very high representative amount of, when you have a certain amount of analyte, you can see a very proportional amount in your measurements. Hasn't quite come up, but it's changed, so I haven't doing to change Mac to PC. So just to summarize, in the considerations, and this is something that we're always thinking about for improving LCMS sensitivity, I think the current, we're hitting up and bumping up against this limit of about 2,500 proteins per cell that I hear of reports in different areas of the community that are doing single cell proteomics. I think this is primarily because of the limitations in the current LC technology. And I think as this improves, we will be able to dig a lot further. In thinking about this, and I know Frank's in the audience, and this is a mention for you, Frank, that when you're thinking about developing new technology, we really want it to be able to go to higher pressures, lower flow with accuracy, so that we can reduce speeds. We can go to low nanoflow with smaller ID and smaller emitters. There's no fundamental limitation here. We can do this. We've done it in the lab. And then obviously really thinking carefully about balancing column length and gradient length. So this is where at the moment we're designing columns for the hardware, but where we really need to be is designing the hardware for these sensitive columns so that we can drive better sensitivity for you guys. And this is just a case study where we've kind of, in my lab where we've done this. So in my other day job when I'm running a lab, one of the projects that we're looking at is in dementia research. And one of the things that we're faced with in dementia research in particular is that we don't have any early diagnostics. And this is a project around trying to identify early diagnostics in a large cohort. Ooh, this is what. So we're actually I won't talk to this because I'd rather leave the questions for time, and I'm more than happy to talk about this study later if anyone would like. But essentially, we have access to a very large volunteer population cohort where we have over 12,000 patient samples sampled twice up to 10 years ago, and they're at age 70, and these have now been followed clinically for the last 10 years. So we know that over 1,000 of these patients now have dementia. And we're going to go back and basically make these measurements. But obviously doing 12,000 or 24,000 samples is quite challenging. And this is where we've actually been designing our own LC system. This is just a custom build in my lab. This is not to do with related to ion optics. We've essentially taken the 1200 LC valve. This is the ceramic valve that Thermo manufactures. We've custom designed a little holder here and just set it up with a little Dynex box. And this system, being quite a simple system, we've been running this Aurora Rapid, this 5 centimeter 150 micron column, has allowed us to run an extraordinary number of samples over the past 12 months. We've now, just over the past 12 months, we've just hit over 30,000 samples acquired. And the quality of this has been quite astronomical. So even with this short column, we're getting some pretty fantastic, this is a urine proteome, for up to 75% of the samples, we're seeing more than 800 proteins with quite a low variability. So this is a platform that we're pretty excited about, but essentially because it required the development of a system that was stable enough to do this. And obviously, we could only have done this with the stability of the timsTOF platform. And I'll just leave it there, and happy to have any questions. So thank you very much.
Thank you for the talk. Claudia has a question. Says, thank you. In your opinion, your pulled emitter, is your pulled emitter and therefore reduced connections currently the main advantage versus the low back pressure of micropillar columns? Do you currently think the non-C18 resins would, I guess the question is, what do you currently think about the non-C18 resins in your column?
I think there's two parts to that question maybe. So the first one, if it's the sort of a packed bed and the differences with what we've got. So absolutely, I mean, she referred to the pre and post column dead volume. These are absolutely essential. So by removing these post column dead volume in particular, you are able to maintain your chromatographic separation. So if you're not doing that, you're not getting the benefit of all the separation that you're doing if you have that post-column dead volume. Pre-column dead volume, you get peak tailing, so you definitely lose, and you lose a lot of intensity that way as well. At the moment, we're only making C18, so we're only packing columns with C18 resin, so we haven't yet packed anything else.
I had a question. So in the 5 years down the line, what do you think is going to be the future of liquid chromatography? It seems like a lot of people are going more towards having really short gradients and increasing throughput in that way. If you're doing small samples, for example, you might want to have low flow rates, but you run into issues with peak sharpness and things like that. How do you think? Yeah,
I think it's probably system miniaturization. So very low swept dead volumes, low diameter columns, small beads, and short gradients. And I think the caveat to that is having an instrument fast enough. So I would love to see, in the next few years, we start seeing sub-second peak widths, but we need to be able to do reasonable quantitation of these. But, so yeah, I think miniaturization essentially of the flow path. Which is challenging. It's a really hard thing to solve.
Thank you for your presentation. You talk about the need of improving LC separation or LC just by itself.
Mm-hmm.
And I saw you were working on the timsTOF Pro. Now with the timsTOF, we have the ion mobility that is also a dimension
Yes.
of separation. Do you think the LC improvement is still as needed as before? Now we have the ion mobility, or do you think it's also a good way to compensate a little bit the lack of LC separation you are expected right now?
Yeah, it's a really good question. I think having the added benefit of mobility absolutely helps. It gives you cleaner spectra. We have less issues with false discovered peptides because of it. Now that Brook are actually incorporating the CCS value into their FDR calculations as well, is fantastic. But to answer your question, I think we absolutely want better separation. It's the best bang for buck thing. The only way that we're going to be able to keep digging deeper and seeing more is by improving the peak capacity.
Thank you.
Yeah, sorry, I forgot to ask for questions in the audience. David?
Thank you. Excellent overview of that and vision for the future. How do you segue the sort of extrapolation you're doing in your mind in the chromatography with the sample volumes and the auto sampler and the sample preparation for single cells? Because one of the things we do, even when we're using nanoliter droplet size prep, is dilute the sample down to avoid matrix related effects, and it may be part of the lysis itself. And then you have all of this mechanics of getting the sample from where you've produced it to the column.
Yes. I think I think we're used to think about things as being in a liquid phase. I think things like EvoSep are showing that you can develop technology where things don't need to remain in the liquid phase. So I would say, maintaining sample abundance, not losing it to plastic and things is absolutely, as you rightly point out, is absolutely paramount. I think it's things like that. I think the EvoSep have got a great platform for this at the moment.
Great talk, Ash. One was interesting. You mentioned the work with a higher degree of Brownian motion, more diffusion for smaller peptides. Is this result in broader peaks for smaller peptides, or is that diffusion stay contained?
Yes, it's a good question, and it's hard. It's actually not one of the. I know exactly what you're talking about. It's the C term, and it's the eddy dispersion. It's not easy to quantify. But so I don't know if you may have read, there's some work that was done by Mary Worth a bunch of years ago looking at slip flow, where it becomes really crucial when you get down to these really low bead sizes, where you start getting these effects being quite transparent, so quite large. So you can see that large molecules aren't affected where small molecules. With the types of chromatography that we're doing now with the bead sizes, once you get below about 2 micron, I don't believe that we're suffering from these things as much at all. Yeah.
I wanted to ask about that. The study sounds really cool with your 30,000 samples from Alzheimer's. Is that run across multiple instruments or all the same color? I guess.
Yeah, so I didn't explain it very clearly, but that 30,000 was all the testing samples that we're doing in the development. So there's about 60 experiments worth there of just getting the experimental prep, the sample prep up and running, everything. We're now only a few thousand in. Yeah, sorry, what was the question?
And I guess also what gradient lengths are you using to run those samples?
Yeah, so it's about a 9.5 minute gradient in 11 minute cycle time. Yeah, so we can get through about a 384 well plate in 2 days on one instrument, and we have 3 instruments that are running.
Yeah, thank you.
Thank you, Andrew. Nikolai Slavov is asking the question. I really liked your optimism about the potential to further increase the sensitivity, improve the separation. If I ask you to speculate about that, would you expect to have significant improvements on the side of improving sensitivity by improving liquid chromatography within the next 2-3 years? What's your view in terms of the time frame over which we are going to see those improvements?
Yes. So I think we're starting to butt up against the limits of the current hardware as it stands. So if you think about the design of current chromatography, so we use piston pumps to control flow at the nanoflow. I think these are good, but probably only good down to about 20 nanoliters per minute. To get down to this range where we start seeing this, we can keep going up on that exponential curve of sensitivity, we need to have flow much lower than that. So I think getting down into the low nanoliter, they've shown from about 10, 12 nanoliters per minute is where you start really losing this suppression effect. And most of the analytes that are there present coming off the column are able to get into the instrument. I don't know, I hadn't put the photo on, but I have another photo of a plume, and 98% of the plume is just going into the front of the mass spec. There's only a few ions that are actually going into the capillary.
So you're emphasizing the challenges with the HPLC pumps rather than the columns themselves, which of course is very important. You need to advance both.
HPLC pumps, but also the swept volume of the system. So we really need to get down into smaller diameters. We use, everyone's using 25 micron IDs. But if you think about the size of the valves and the volume in the valves, pre-column volume, all of these things we need to be able to try and shrink down.
Thank you.
Hi, thanks, very informative. So indeed, the longer the gradient and the higher the back pressure, the problem we've been experiencing is the fact that you have this long gradient delay because you have to run lower flow rates. What are your thoughts about flow ramping, kind of like EvoSep does or the micropack Vanquish allows you to do, and how can we incorporate that with such low bead particles and smaller ID columns?
Yeah, so I mean, it assumes that you have a nice range above your gradient pressure that you're running. So in the system that we've set up for the high throughput, we run about a 1.5 microliter flow rate, which gives us about 200 bar. We ramp that up to about 800 bar for loading, so we go to 6 microliters a minute. So I'm a big fan of using high pressure for load and re-equilibration to really squeeze in. So I think what EvoSep have done, Webb followed suit, and these methods I think are now reasonably standard on the Neo Vanquish as well. So you can do these sort of very fast maximum loading. It sort of goes back to the days of the Easy Nano LC where they did this pressure loading. I never liked the pressure loading. I quite like having some sort of flow control, just so you have a bit more control over what you're actually putting through the column, so it can be more consistent run to run. Huge.
If you have your 20 micron ID, you can never get up to those high flow rates. So how are you guys going to solve that?
Well, that's where we need to go to push much higher pressure.
Good luck getting the right valves for that.
Yeah.
Thank you.
Pleasure.
Thank you for your call. Just an additional comment about that. You spoke mainly about sensitivity and separation pore, but I think robustness and throughput is really important in single cell, of course. So when you reduce the sizes like this, of course, the reconditioning is more longer. That's one point. And I was wondering also if you think about providing pre-column in such a way that you can clean up online the samples to have more robustness for a lot of samples to be analyzed.
Yeah, I might answer the second one first around sample cleanup. So I'm a big fan of doing sacrificial C18. So whether you're doing a stage tip, in this process, we're doing 384 well plate processing with magnetic beads. We're doing a peptide sample cleanup, and that C18 will go in the bin. And we often think about this as desalting, and that's protecting the instrument, but actually what's protecting is the head of the column for the things that are going to go onto the column and not elute. So you've essentially pre-cleared your sample. The first thing you mentioned, I wasn't sure if there was a question there.
When applying low flow, the reconditioning is longer.
Yes.
And also when you use longer columns. So what about the throughput?
Well, I think when you start shrinking down, I think you can go, when you're going smaller bead sizes, smaller diameters, I think we're going to have much sharper, much faster gradients. I think we'll be down sub 5-minute gradients, but having a peak capacity of where if you're running a 75, 50 centimeter, we're basically shrinking that peak capacity into a much shorter space. But this is where, as I mentioned, the TOFs are probably only things fast enough to be able to sample across a sub-second peak. Okay. Yeah, I think as you scale down, the speed, you end up speeding up.
Yeah, okay. Thank you.
Any more questions from the live audience? Yeah. Okay, I think this is the last one.
This is Peter Nemes. Just a very quick question, more about practical side. So as you go to really low flow rates, the quality of connections becomes increasingly difficult to maintain in the laboratory. Could you tell us a little bit of from your lab's tricks on how to ensure that connections are proper everywhere along the LC-SI setup?
Yeah, so I
What
mean,
challenges would you usually encounter and how do you solve them?
so in all of our systems, we've been using nanovipers, but actually, I think the quality of the nanovipers, I shouldn't say it publicly, I haven't been as happy with the quality of the nanovipers in recent years. And it's something that we're looking at actually as a company. So we're looking at alternative solutions, but where we have high pressure fittings with very low dead volumes. I think gone are the days, if you're still trying to fit and use your own things, I'd go and use the nanovipers. I know they're a bit more expensive, but then you do get away from these problems of leakages. But this is where we need to be working on this technology. We need new ways of interfacing very small volumes that allow for high pressures. I don't have solutions for these things yet, but I'm pretty committed to trying to work on these so I can lift the capacity of what you guys want to do with single cells.
Thank you.
Pleasure.